The beach is a great place to relax. It's fun to collect shells, watch the migrating birds, or just look out on the seemingly endless ocean. It's also a great place to think about the nature of our world. We know that the world is made up of atoms, but we can never really experience individual atoms. The air, for instance, is a mixture of free-flowing gases that I feel as a breeze, and the oceans flow uninterrupted from shore to shore. Even though we know that liquids and gases are made up of atoms, what we see and feel is a continuous substance. And the sand beneath my feet feels solid and continuous. But it's really made up of tiny particles. A grain of sand is about the smallest piece of matter I can see without a microscope. But as small as it is, it still doesn't give me a clue about the nature of the atom. Our world is made of atoms, but we can't observe individual atoms. What we observe is a continuous liquid, or a gas, or a solid.
Matter comes in so many forms that it defies simple explanation. Imagine how bewildering this must have been to early chemists. Sodium, a very reactive metal, and chlorine, a poisonous gas, combine to form a substance that is common and vital to life, sodium chloride, better known as table salt. By the middle of the 19th century, scientists understood the difference between a compound and an element. Some 60 elements had been discovered, and many of their chemical and physical properties were known. Scientists searched for a pattern that would somehow relate elements to each other. List some characteristics that might be used to organize the elements. Some chemists tried to arrange the elements according to qualities like color, texture, or hardness. But elements that are similar in appearance may have very different chemical properties. Elements are so diverse and exist in so many physical states and compounds that a pattern was elusive. Only when chemists began to look at boiling point, freezing point, density, and the reactions of elements forming compounds did meaningful patterns become visible. Explore some of these patterns now.
When the elements are arranged in order of increasing atomic mass, patterns appear for some physical characteristics.
One aluminum atom bonds with 3 fluorine atoms to produce a crystalline salt.
These elements also behave similarly when combined with sodium. One atom of each of these elements combines with one atom of sodium to produce a salt. Each of these elements combines with fluorine gas. As you view the reactions, watch for a trend. Fluorine gas enters through the tube at the left and reacts with sodium. Fluorine gas enters through the tube at the left and reacts with magnesium. Aluminum powder is placed into a jar of fluorine gas.
Silicon powder is placed into a jar of fluorine gas. Fluorine gas enters through the tube at the left and reacts with phosphorus. Sulfur powder is placed into a jar of fluorine gas.
What is the trend? The number of fluorine atoms combining with these elements increases as atomic mass increases.
Lithium, sodium, potassium, rubidium, and cesium are very similar metals. They are so soft they can easily be cut with a knife.
We'll start with lithium. The metal floats on the water and reacts with it, giving off hydrogen gas. Now for sodium. The same sort of thing happens, although the reaction is a bit more vigorous. Now for potassium. This time you'll see a flame. The heat given out by the reaction is produced so quickly that the hydrogen gas catches fire. It burns with a lilac flame. The next element is rubidium. This time we put a safety screen between us and the reaction. Let's try cesium.
Here are the elements arranged in order of atomic mass. How does atomic mass relate to the level of reactivity with water?
We'll start with lithium. The metal floats on the water and reacts with it, giving off hydrogen gas. Now for sodium. The same sort of thing happens, although the reaction is a bit more vigorous. We'll start with lithium. The metal floats on the water and reacts with it, giving off hydrogen gas. Now for sodium. The same sort of thing happens, although the reaction is a bit more vigorous. Now for sodium. The same sort of thing happens, although the reaction is a bit more vigorous. This time you'll see a flame. The heat given out by the reaction is produced so quickly that the hydrogen gas catches fire. It burns with a lilac flame. The next element is rubidium. This time, we put a safety screen between us and the reaction. Let's try cesium.
As atomic mass increases, the violence of reaction increases for these elements.
Dmitri Mendeleev and Julius Meyer were the first chemists to discover a systematic pattern, or periodicity, in the elements. Meyer looked primarily at physical properties. Mendeleev had a vast knowledge of both physical and chemical properties, but he gave priority to chemical properties. They independently found the periodicity of elements and charted these patterns into nearly identical tables. In 1869, Mendeleev published his periodic table and went even further by inducing a periodic law. He used this law to predict new elements that had not yet been discovered.
Mendeleev wrote the elements on cards with their atomic mass and physical and chemical properties, and began a sort of game that his friends called patience. He laid the cards down in rows according to atomic mass, beginning with the lightest. Hydrogen seemed to have unique properties, so he put it aside. Helium hadn't been discovered, so Mendeleev began with lithium, then beryllium, boron, carbon, nitrogen, oxygen, and fluorine. The next heavier element is sodium. Experiments show that sodium and lithium have similar properties. Where would you place sodium? To keep elements with similar properties in columns, Mendeleev started a new row with sodium. He then continued with magnesium, aluminum, silicon, phosphorus, sulfur, and chlorine.
This sequence follows atomic mass, but density, freezing point, and boiling point also support this pattern. Chlorine shares many characteristics with fluorine. They are both gases, both react violently with sodium, and the compounds they form are very similar. Potassium is like lithium and sodium in many ways, so Mendeleev began the third row with potassium. Mendeleev continued placing elements in rows according to atomic mass and in columns according to similar properties. This worked fine until he came to titanium. Titanium doesn't share chemical properties with aluminum and boron, but it does with silicon and carbon. Mendeleev faced a chemical quandary because if he put titanium under aluminum, the periodicity of his table was broken. What do you think he did? Mendeleev decided to leave a gap, an empty space in the table. What did this empty space represent?
Mendeleev recognized that the gap was not a flaw in his scheme, but an undiscovered element. This demonstrates his genius and shows the difference between discovery and synthesis. Mendeleev discovered the periodicity of the properties of the elements, but it took his immense knowledge of the elements and his imagination to synthesize to create a periodic table.
As he continued, he found more gaps, and in some of these gaps he placed elements from his own brilliant imagination. His most famous prediction was here, in the same group as carbon and silicon, and in the same period as copper and zinc. He called it ecosilicon. He estimated its properties by averaging properties of the elements above and below and left and right of the gap of his table. You try it with the elements that surround it on the modern periodic table. Here are Mendeleev's predictions for ecosilicon. In 1871, this element was discovered and was named germanium. The chemical and physical properties of germanium matched Mendeleev's predictions almost exactly. The arrangement of the periodic table showed that an element's atomic mass is systematically related to its chemical and physical properties. Mendeleev proposed a periodic law. When arranged in order of increasing atomic mass, elements exhibit similar properties periodically. Mendeleev encountered a discrepancy in his system. Tellurium in the 6th row with atomic mass 127.6 AMU should follow iodine with an atomic mass of 126.9 AMU. But chemical properties suggested that iodine belonged with fluorine, chlorine, and bromine. Mendeleev felt that chemical similarity was of greater importance than mass, so he reversed their order to maintain periodicity. Mendeleev's periodic table has been revised many times to include nearly 50 additional elements that have since been discovered. When the noble gases were discovered, they fit the scheme well since they all display similar characteristics. The table was also adjusted to better show the transition elements. Even with these additions, Mendeleev's basic arrangement and assumptions remain valid.